Hello class, welcome to this video on AP Statistics, lesson 3.3, transforming to achieve linearity. So in this lesson we're going to look at transformations, various transformations to take data that is nonlinear in order to make them linear. So we're going to start with a couple examples to kind of show you the nonlinear nature for some of these graphs. So here below shows the concentration of a chemical compound in units of molarity over time in seconds. All right, so we have the concentration of the compound over here, and then the over time. Okay, and we have, the table shows as a stacked table because, we have a lot of data points. So here we have a total of 12 data points of time versus the concentration. So we have the explanatory variable, which is time, and then the response variable is the compound concentration. And so what we're doing is we're going to graph these data points in a scatter plot, and we have here concentration versus time, and you can see that this is a curvilinear, so it's non-curved. I mean, it's non-linear, which means it's curved or curvilinear. And so if you look at the shape of the curve, it looks to be increasing. However, the rate of increase is actually decreasing, meaning it's flattening. It's eventually approaching, what looks like a threshold. It's getting flatter over time. And however, it is curved, and if we look at it, due to various factors, it has been increasing, but like we said earlier, the rate of increase is actually decreasing. And so what we're going to do is we're going to try to straighten this curve out. So what we're going to do is we're going to take the natural log of the time. So if we take the natural log of the explanatory variable, which is the time, then we can actually linearize the data. So using a logarithmic transformation. So in this example, using the logarithm of the time seems to straighten things out, as you can see in the graph. All right, so we're going to show you another example of taking a curve and linearizing it, or trying to achieve linearity. So let's look at another chemical reaction where we have a chemical compound, its concentration over time. Here the chemical compound is decreasing. So in other words, this is sort of like a reactant, and a reactant is decreasing in concentration as the reaction proceeds. And so if you look at the concentration over time, it's been decreasing. However, the rate of the decrease of the concentration has been decreasing as well. So it first starts out kind of steep, right? And then it kind of, has that leveling out effect. So again, this is actually an exponential curve. So it's actually a negative exponential, right? It's decreasing. And so what we can do is take this exponential curve, a nonlinear or curvilinear form, and we can do a transformation. This time we can do a logarithmic transformation on the response variable, on the concentration. So this is a first order reaction. So if you have taken chemistry, this first order reaction is the logarithmic transformation. So it's the natural log of the concentration over time gives you a straight line. But here's another example of a transformation, this time applied to the response variable. All right, remember that doing the logarithmic concentration of the response variable is the same thing as doing the opposite transformation on the explanatory variable. So in this case, instead of doing the logarithmic transformation of the response variable, I could do an exponential transformation on the time variable, and that will be the opposite effect of this logarithmic transformation. But if I do the exponential transformation on the time instead, it'll give me the same linear form that we're looking for, because we mentioned earlier that this is an exponential curve. All right, so again, using a logarithmic of the concentration seems to straighten things out, and we're going to look at some more details of that and how that works. So first off, the transforming the data amounts to changing the scale of the measurement. So in this case, in the previous two examples, we used a logarithmic scale, right, essentially by doing that transformation. As we change that scale, that allows for the data to be linear at that point. So changing the scale that was used when the data was collected enables us to linearize the data. So let's take a look at the power model. So this is the The traditional power model, which is like a curve, like a polynomial curve, right? Where n is the power and a is the coefficient. So in this case, if n is 1, then we got a line, right? If n is 2, then we got a quadratic. N is 3, we got a cubic function. So this is the traditional power model. So in a power model, if we transform the values of the explanatory variable x by raising them to the nth power, then what we can do when we transform this, we can graph the points x to the n and y. Now, if we graph the points x to the n, instead of just traditionally xy, right? If we just do x to the n, meaning we transform the x values by raising them to the power, then that actually allows for the curve to be linear. So for example, if I have a curve or a set of data points that it appears to be cubic, right? So maybe this appears to be a cubic form. Let's just say x to the second. Let's just say it's quadratic. Well, then what we can say is, well, our power model is y equals ax to the second power, and if we take each of these points, right, each of these points x, y, and we instead do a transformation where we turn them into x squared y. So if, for example, one of the points was 1, or like 2, 4, right? Because 2 squared is 4. Let's just say it's y equals x squared. Then we get 2, 4. Then when we use the transformation, this would be 2 squared, right? So 2 to the second is 4. So it'd be 4, 4, right? Where this becomes 2 squared. So, and then if I do that and I plot all those points, well then each of those points, so this point which is now 4, 4, right? Which is x squared y, will enable the points to follow a straight line. Okay, so that's the main idea anyways. All right, so what we want to do is look at an example in which we have a polynomial or some kind of curve and see if we can linearize it. So here in a fishing tournament, prizes are given out for the heaviest Atlantic Ocean rockfish that is caught. The fish that are caught are released after their lengths are measured. So they take the fish, they measure the length. They don't want to use the scales to weigh the fish because, you can imagine in the competition, once they catch the fish are going to be moving around, and it's not going to be very good if you're trying to measure the weight of the fish, right? Especially with very accurate scales, and you're on a boat as well. So what we want to do is we want to just determine the weight from the length. So we measure the length real quick, and then we can release the fish, and then we can calculate what the weight would have been. The organizer finds data from a marine research laboratory to provide reference data on the length. So we got to get some reference data so that we can use that to calibrate, to figure out what our weight could be based on the reference points. All right, so the scatter plot of the data is given below. Computer software are used to perform a regression analysis of y equals weight versus x equals length cubed. So right now this is telling us that we assume, or we're thinking, that the data seems to be cubic in nature, right? A cubic function looks like that, right? Where it starts at 0, and has that form. So we're thinking it's some kind of cubic looking function. Of course, we don't have a negative because it doesn't make sense to have negative length, right? So we just have the positive version of that. So we're thinking it's cubic. Why? We'll find out later in the lesson why we think it's cubic. But for now, let's just assume that by geometry, this is a cubic function, and so we perform a computer analysis of the results, okay? And so what we're going to do is we're going to take resummarizing what we just had, the data here in the scatter plot. We want the equation of the least squares regression line. Define any variables that you see. And then part B, suppose a contestant in the tournament catches a rockfish that's 36 centimeters long. Use the model from part A to predict the fish's weight. All right, so let's look at the first part. Find the least squares regression line. We're going to use that from the computer analysis results, okay? So first off, because this is weight versus length cubed, we're going to use the computer analysis. We're going to say, okay, well, we got the constant here. We're going to be using these two things, right? The coefficient and then the slope, right? So this is the y-intercept. This is traditionally my a, right? And then this is traditionally my slope, right? a plus bx, right? Because remember that the equation y hat equals a plus bx, right? So we're going to do that, but remember, we're going to remember that x is cubed, right? So we're going to plug it into that, but keeping in mind that this is length cubed, right? To the third power. So we literally just plug in our a and our b into our linear regression model, but just remembering that x is cubed. So y hat is the predicted weight in grams, and x is the length of the fish in centimeters. And of course, we cubed that in the model. All right, so hopefully that made sense. That's the equation of my, my least squares regression line. Now keep in mind that this is a cubic model, but it becomes a least squares regression line when you essentially replace this with your traditional x, okay? So in this case, we have our traditional x, so y hat equals the 4.06 plus 0.01467774, you know that, and then this is sort of like my new x, and then so then that becomes a straight line where we just realize that this x is actually cubed, okay? So just so that you're aware, that's what we mean by that. So suppose a contestant catches a 36 centimeter long rockfish and use the model to predict the fish's weight. So we're going to take the model that we had. Now remember that this is 36 cubed, right? So we're going to keep that in mind. And so we get a prediction of 688.9 grams if we plug it into the model. All right, and that's really all there is to it. That's part A and B. Once we get the computer model, it'll take care of it for us. All right, so we're going to take the traditional weight length, right? This is the original data, which we know it follows a cubic model, and we're going to graph the points x cubed and y, right? Because we're going to take each of these points x, y, and we're going to transform it, right, using the cubic model, the ax to the third model, and we're going to say, okay, x cubed y. We're going to put it to that transformation, and that should give us a graph that is approximately linear, right? You can see that from the data. All right, so now we're going to take that linear form. So this is the linearized points. These are the points x cubed y, right? And or rather, these points themselves, the x cubed y comes from this line of best fit, right? The regression line. And so we're going to take each of those and put it on the left side. And then what we can do is we're going to compare this. How does this look like if instead of cubing the x, I cube root the y? So so notice that this is to the third power, and this is just regular y, right? So this time what we want to do is, what happens if we instead just leave this as x, right? But then take the cube root of the weight instead. How's the data going to look like? Well, if we do that, it's going to be linear as well, but obviously it's not going to be the same. It's not going to be the same line because it's a different model, right? It's a cube root model. But here is how it looks like if we take the cube root of the weight versus the length. Notice the linear nature. It still has the same linear form. However, the y-intercept and the slope are different. You can see that from the scale. Definitely things have changed here as far as that's concerned. But we see a linear form. So we're going to show you how to do the scatter plot on the TI-84 calculator. This is for the original data. Okay, so we're going to make the scatter plot of the original data so you can kind of see how it looks like to do the scatter plot. All right, so here we go. So we're going to hit stat, and we're going to hit edit. We're going to type in our x and our y values, the length and the weights, into that table, into L1 and L2. We're going to quit out of that. Then we're going to hit second y equals, and we're going to go to the first one, enter that. We're going to hit on. We want to turn that on. We're going to go to the type. That's the scatter plot. That first option is the scatter plot. Then we can quit out of that. We're going to hit zoom and then go down to 9 for zoom stat. You can enter, and you can see our original scatter plot, which matches our the model from the original. You can see them side by side. Now we're going to show you the scatter plot for the transformation, for the x cubed transformation. So let's show you how that works this time, and it's going to look like the graph on the left, on the bottom left, when we do this. So I'm going to show you how to take all of the data and cube the x values, right? So for example, if I take this weight and I raise it to the third power, right? I do this 5.2 to the third power, right? And I do that for all the points. How do I do that on the calculator? So I want to show you how to do that. So first off, let's go to our stat edit just to look at our lists, L1 and L2, make sure that those are inputted. Now we're going to go to L3. We're going to use L3. So let's quit out of that first. We're going to go to second stat. And we're going to do L1 raised to the third power. That takes the x values and cubes them. We're going to store that into second stat L3. All right. So that's my L3. And now my third list has my cubed data for my x values. So that L3 has my x values cubed. All right. That's what that is. So we're going to quit out of that. And then we're going to go second y equals, go to this plot, stat plot. We're going to turn that on, use the scatter plot option, take the x list and put second stat, go to L3 because that's the cubed data that we did. All right, and then we can go to zoom. We want to quit out of this first. So let's quit out of this and then go to zoom 9, right? Zoom 9 for zoom stat. And there you go. There's our linear form that you can see side by side. So again, we took the L3 for my x values because we cubed the x values earlier, right? So that's what we're doing. We're doing that transformation. All right, so now let's look at how to do the least squares regression, right? So, so basically, how do we get the linear, the coefficients for the least squares regression model if we cube the data, right? Like if we do x cubed, how do I get the a and the b, right? Because we know that the equation is of the form y hat equals a plus bx. So first we got to check our list. We have our cubic list, L1, L2, L3. We're going to go to the stat, and we're going to go linear regression, change the x list to L3. And then we're going to go down to calculate, and there it is. Our A and our B. Now remember that our A and B are switched, right? So this A on the calculator is actually our B in this model, right? And this is actually our A in the model. You can see that right there. So they're switched. A and B are switched on the calculator. I know it can be confusing because the calculator goes traditionally AX plus B, but traditionally in stats we go A plus BX. And the reason why we do that, by the way, is because when you do a regression for higher order powers, we do A plus BX plus CX squared plus DX cubed plus EX to the fourth, and so on. So if you go to multi, regression, right? So for higher orders, that's how we do it. We go in an ascending order of powers of X. So that's why we do the AB method like that. Okay, it's not arbitrary, and that's why we do it. All right, but there you go. That's how you figure out the least squares regression coefficients. All right, so let's look at going back to the Atlantic Ocean rockfish example. This time we want to look at the cube root, right? So we know that cube rooting the y values, right? The weight, that's going to lead to a linear form as well. So what happens to the coefficients if we cube root the weight? Well, as you can see, we got different coefficients here. We got a coefficient that's a constant and a length. So the y-intercept and the slope are both different than it was last time. So let's find out the equation of the least squares regression line, and then let's make the same prediction for 36 centimeters. All right, so for part A, again, we're using these two. That's my A and that's my B. I'll put those into my regression model. But keeping in mind that I'm doing the cube root of the weight. So that's the cube root of y, right? So that's the cube root right there. So, and we're using y hat, right? Because y hat is a prediction. So the cube root of y hat equals our a plus bx. So here we're keeping x constant. How do we know x is constant? It's because it's just regular length. That's my x, right? We're not doing length cubed or anything like that. All right, so that's my model. Y hat is the weight in grams and x is the length of the fish in centimeters. And so this is sort of like my traditional y, right? In quote unquote. So y equals a plus bx. So it's a linear form if you graph it like that. All right, so suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. So because we have the cube root, we have to keep that in mind when we do our answer. So we got the cube root equals our a plus bx, but this time we're replacing x with 36 centimeters, right? So we got that right here. And so when we do that, we get 8.856. But keep in mind that this is the cube root, right? So the cube root of y hat is 8.856. So how do we get y hat? Well, we got to take we got to cube both sides. We got to raise both sides to the third power. That's the only way we can get rid of that. Okay, and so y hat is equal to that cubed. So that's what we do. We cube the 8.856 and we get 694.6 grams. All right, so pretty close to what we had for our prediction before. All right, so that's A and B. And now I'm going to show you how to do the cube root, right? So we showed you how to do x cubed. Now we're going to do the cube root of y, all right? It's pretty similar, but this time we're doing it to y instead of to x, right? And we're doing cube root. Okay, so let's go to show you the steps here. So let's go to stat, edit, make sure you have your L1 and L2. We're going to put cube root of y under L3. So let's quit. I'm going to go to math. Then I'm going to go to number 4 for cube root. All right, now I want to cube root the y value. So I'm going to go to second stat. I'm going to go to L2 because that's my y values. So I'm going to do the cube root of the y values, store that into the list 3. All right, now list 3 is going to have my cube rooted y values. Now I'm going to go to stat, edit. I'm going to show you the L3. That's my cube root y values. I'm going to quit out of that. I'm going to second y equals to stat plot, turn that to on, use the scatter plot there, then go to zoom, or we can quit or change that x list. I'm going to change it back to L1, right? I'm going to go to y list. I'm going to change that to L3 because the y values are changed. All right, and then I can quit out of that, zoom 9, and there is our linear form scatter plot, okay? And that's for the cube root of y. All right, so hopefully that made sense. Now we're going to show you how to get the least squares regression model, right? So this time for the cube root of y hat. So let's show you how to do that. So first we're going to go stat, edit. Let's make sure that you have your L1, L2, and L3 just like in the previous steps. Let's quit out of that. Let's go to stat, go to calc, go down to linear regression. Again, do the X list, change that with second stat, change that to L1, change the Y list to L3. Go down to calculate, and there it is. There's our values, keeping in mind that they're reversed, right? So we got our A value here is actually our B in our model. Our B value here is actually our A in our model. All right, so hopefully that made sense, and those are the same exact results as from our computer output. Okay, so transforming with powers and roots. So to achieve linearity when working with a power model of the form y equals ax to the n, you can transform the data by, first, you can raise the values of the explanatory variable x to the nth power and plot the points x to the n y. And once you plot that, it's going to transform the data and it's going to linearize it. The second thing, you can take all, this could be an or, right? So, or you can take the nth root of the response variable and plot the points x and then the nth root of y. All right. So if you're doing for example, a model of y equals ax to the 4th power, then this would be x to the 4th y, right? And then this would be x 4th root of y, as an example. All right, so let's show you how to transform with logarithms. So with power models. So when looking at the data that follow a power model, this is how we're going to show you how to find the nth power, right? So before I said or asked you, well, how do we determine whether it's to the third power, to the second power, to the fourth, right? So what we can do is we can transform this using the logarithms. So if you don't know the value of n, what we can do is you could do the scatter plot of the logarithm of both variables. If you take the log of both variables, x and y, it'll produce a linear pattern. Why? We're going to show you now. So remember that you're going to need some basic logarithmic properties from Algebra 2. So we're going to take the log of both sides, right? The logarithm of both sides. And then remember that this logarithm can be split up into a sum because we got a product inside the logarithm, which means we can express it as the sum of logs. And so we have the log of a plus the log of x to the n. Also, remember the property that if we have a log of a number raised to a power, we can bring the exponent down as a coefficient, right? That's one of the properties of logs. And so you can see if we we can treat this as a linear function, treat the log of y, and then actually we're going to just move this around. We're going to put the log of a last, so you can kind of see we're going to put this first. We're just rearranging some terms, and we can kind of show you that it's linearized in the sense that log of y can be treated as y. The log of x can be treated as x, because remember those are transformed x and y's, right? We transform those by taking the log. And the n, the exponent, is actually the slope of this linearized form. And we got log of a is our y-intercept. And so if we were to graph this model, we can see that the slope of that line of best fit is going to actually give me my exponent n. So again, just to kind of show you those, and I kind of color-coded those for you. If we compare the equation to the slope-intercept form of a line, the value of n is the slope of the regression line of the data. So if, for example, I have a bunch of data that looks like it has maybe a linear form like this, and I do this transformation. I do the transformation on log of x and y. And so then if this is y and this is x, well then let's assume, I'll just show the transformation here. Let's say we did log of y over log of x. And then let's say we end up getting something that looks like a straight line, right? Well then the slope of this line, if the slope of this line is, for example, 2, then that's telling me, right, the slope is 2. That means that the model has to be ax to the second power. All right, so that's how you determine that, by once you take the logarithm. All right, so let's look at an example. So in the preceding examples, we used powers and roots to find the model. We said it was y equals ax to the third based on geometry. But now let's go ahead and take the log of base 10 of both sides, of x and y rather, and then do a computer analysis, right, to give us the coefficients. All right, so we took the log of x and y, and notice we get something that looks linear, very linear, in fact. We're also looking at the residual plot. The residual plot tells us the nature of the data as well. Is a linear model appropriate? Obviously, based on this, it looks pretty appropriate. However, we want to make sure that you know how to actually look at a residual plot to determine whether a model is appropriate or not. So here we're going to notice that it looks pretty random. There's no pattern to this, right? It looks pretty random, up and down, down, up, whatever. And roughly 50% is above, 50% is below. Again, it doesn't have to be exactly 50-50 because remember, it's by chance. So it's just by toss of a coin. So if you were to toss a coin, heads being above the line, tails being below the line, it should be, pretty random. And it looks to be random in this residual plot. Okay, and we got a computer analysis of the log of the y versus the log of the x. All right, so first thing, based on the output for the residual plot, explain why it would be reasonable to use a power model to describe the relationship between the two. And then we want to give the equation of the regression line, the LSR. Be sure to define the variables, of course, and then make the same prediction as we made in the previous two problems for 36 centimeters. All right, let's go. Part A, as we mentioned earlier, if we were to plot the residual plot, we can see that if we do the scatter plot, it looks like it's a linear form. The residual plot supports this by showing random scatter of points about the zero line. Therefore, a power model seems reasonable here. So we know we can use a power model. Now, what is the exponent for the power model? Well, remember I said that the slope here tells you the slope of the LSR, the least squares regression line, is going to tell you the power of the model. This looks to be about 3, right? So this is approximately to 3, which means it's demonstrating that our power model is y equals ax to the third power. So it's approximately cubic. You can also say 3.05, but again, that's close enough to 3 that we can just say ax to the third power, right? Because remember, 3.05 is not going to be a power model anymore. N has to be an integer for this to work, right? So it has to be 1, 2, 3, or so on, right, for it to be a power model. So that's about 3. Okay, so a power model seems reasonable here. So for part B, give the equation of the least squares regression line. All right, so let's do that. Let's use our two coefficients. Remember that we're doing log of weight versus log of length. So we're actually doing log of y hat and log of x, all right? We're saying y hat for the model. This is actually log of y, but when we do the model, we need to include the log of the y hat. All right, so remember the log of both of them. And then we're using our coefficients from here and here. All right, so that's our least squares regression line. It's our equation. And so part C, we're gonna use the prediction of 36 centimeters. So we're gonna plug that in for x, right? So x equals 36. So we're gonna do, obviously we're gonna do the log of 36, right? So let's do that here. So plugging that into here, that's gonna be the log of 36. All of this equals to the log of y hat. So we do the formula, or when we plug it into the model, we get 2.8464. Now remember that in algebra 2, if we wanted to solve for y hat, or if we want to get the variable by itself, remember we have to keep in mind that the base of the log is actually 10. It's an invisible 10. If it's just written as a log, log, just like that with no base written. And so we have to assume that's a base of 10 there. And then remember, the opposite of a log is an exponent. So the only way I can get rid of this log is by exponentiating both sides. So we got to take the base and raise it to both sides. So we're going to take 10 raised to the left side. And then whatever you do on one side, we have to do on the other side. So the other side is going to be 10 raised to the 2.8464 power. So we had to exponentiate, turn it into an exponential on both sides. All right, and that's going to cancel out the log here, leaving us with y hat equals 10 to the 2.8464 power. All right, and that's how we get that there. And so doing that on the calculator is going to be a number between 100 and 1,000, okay? So, which is 702.1 grams. All right, remember that our previous prediction was about 694.6 grams. So they're ballpark more or less about the same, right? High 690s, low 700s. So our prediction using all models seems to be about the same. However, it must be noted that this is a more accurate model in the sense that we actually use this entire number rather than using x to the third power. We're using this whole number right here, right? So keep that in mind that we're actually using the entire all the digits for the power as well. All right, so that's how you determine the power and using the transformation there. So let's show you how to do this for log of y versus log of x to do the scatter plot. So if I want to do a transformation of the log of the y and the log of the x, how do I do that? So first you got to make sure that you have the x and your y data. So let's go to stat, edit, make sure you have your x and y data, just like normal. We're going to do L3 and L4 for the logarithmic transformations, okay? So we're going to quit out of that. We're going to go to, we got to do the log. So we're going to do the log and then go to our list. So second stat, we're going to do L1. So we can take the log of the x data, close parentheses. We're going to store that into L3. So second stat L3. So the x transformations are going to go in L3. All right, so that's the log of the x's. Now we're going to go to show you the L3. That's my x values transformed. Now we're going to do the log of the y values. So second stat, your y values are L2. We're going to close that, store that into L4 using second stat 4. There you go. So now L4 has my transformed y values. All right, I'm going to show you those values now so you can kind of see them. All right, so now we're going to quit out of that. We're going to go to second y equals, turn our plot on, and use the scatter plot option for the type. We're going to change the x list to L2, or L3 rather, not L2, sorry. And we're going to change our y list to L4. So L3 and L4. We're going to zoom, stat, and there is our linear form scatter plot with transformations for log of y and log of x. And again, we used L3 and L4 for our transformed x and y values. Okay, so let's show you how to do the LSR, the least squares regression, for the log of x and log of y. Okay, so first you're going to need to know, you're going to need to have done the previous steps that I showed you for doing log of x and log of y. So make sure that if you go to your stat edit that you should have your L3 and your L4 for your x and y's, your transformed x and y's. So quit out of that. All right, so we're going to go to stat. We're going to go to calc, down to linear regression. All right. And then we're going to go to change the x list to L3 and our y list to L4. All right, and then once we do that, we can calculate, and there is our least squares regression line. All right, so you can see that, remember it's reversed, so this is actually our B, and it goes, I forgot to put the regression model from before. Oh, actually, well, you can see it. You can see it here anyways. So our A is actually our B, right? Our A is actually our slope, 3.04, and then our B is actually our A. So you can kind of see it's reversed there. All right, and again, we're not using y, we're using the log of y, right? So it's log of y hat actually equals our A, right, which we have there, plus our B, and then log of x, all right? So just keep that in mind when you do your regression line. All right, so transforming with logs. Let's look at exponential models. So if x and y have a relationship that can be described by an exponential model of the form ab to the x, y equals ab to the x power, that's a traditional exponential model, then a scatter plot of the logarithm of y versus x should produce a roughly linear association. So first off, if you have something that you think is exponential, then simply take the logarithm of y. So do log of y versus regular x, okay? So just take the log of y. It could be a natural log or it can be a regular log. We just tend to do regular log, but you can do a natural log. It doesn't matter. It could be any log. But again, you know, just use regular log. It makes it, you know, just to keep it the same. All right, so here we go. If we use the properties of log, we're going to take the log of both sides. We're going to show you that this gives us a linear model. It linearizes this. because of the wonderful properties of log, right? So log has wonderful properties that we can exploit. So again, we can turn this into a that's a product, so we can turn that into a sum of two logs, and then bring the x down as a coefficient. All right, and then we're gonna just kind of switch these two. All right, and then we're actually going to switch the position of x and that, right? So that we're going to put the log of b as the coefficient, okay? Because log of b is the constant and x is the variable, right? So then if we compare that to the traditional, slope-intercept form, we can see that the log of b is my slope. And so if we find the slope of the least squares regression line, so if we have if we did the transformation, we get a line that looks like that. The slope of this regression line, m, gives us our log of b. So what if I wanted to get b instead of log of b? Well, remember, you can solve for b by exponentiating both sides. So if this is a log base 10, then we can raise both sides to the 10th power. And so we get that b is actually m to the 10th power, all right? So is the slope raised to the 10th power, and that's how you would get the b. If we wanted to convert it into an exponential model, that is. And in the y-intercept, right, whatever that y-intercept is, let's say that y-intercept is, let's just use another number. Let's just say that y-intercept is c. Then that y-intercept c, whatever that value is, that's going to be equal to the log of a, right? And so if I wanted to get a, well, then I would just have to do a is equal to c to the 10th power. And that's going to give me my a, all right? So that's how I get converted over to the exponential model. You don't really have to do that. We only care about using this regression form anyways, but I just want to show you how to do that mathematically. Again, we're just doing this to show you that we can show mathematically that it linearizes the data by taking the log of both sides, so that we can get log of y. But notice that x is not transformed at all, right? It's only y that's transformed. All right. So in this case, let's look at a different example, an exponential example. This is actually known as Moore's law, which is it's an actual law, right? So, and it's saying that, and it's basically predicting with the technological advances that we've had in the number of transistors that we used. Transistor is can be miniaturized, so you can put billions of transistors on a integrated circuit chip. And the amount of transistors that we've been putting in our chips has been doubling every 18 months. As we want to fit more transistors into it to make it more efficient, right? To pack it to get a smaller factor, right? A form factor for the the technology. So this is called Moore's law. So one way to measure the revolution in computing. So it says it shows the growth in the number of transistors has doubled, it's showing the number of transistors from 71 to 2016. And so notice that the years since 1970 is my explanatory variable. My transistors in billions is my response variable. So if this law is correct, then an exponential model should describe the relationship. And so what we can do is we can take the natural log of the response variable, which is the number of transistors. So we could do a logarithmic transformation, take that and take the logarithm of the y versus x, right? And that will give us something that's approximately linear. You can see that. So it has a linear form to it. And we got some computer output for that. So here, this computer output assumes that we're doing the natural log. So this is the natural log of y, right? Computer output. So let's go ahead and take a look at that then. So explain why it would be reasonable to use an exponential model to describe the relationship given. And then give the equation of the least squares regression line, and then make a prediction for the number of transistors in 2020. All right, so let's take a look. Explain why it'd be reasonable to use an exponential model. So first off, you can see the scatter plot of the natural log of transistors versus the x has a fairly linear pattern. Therefore, it's reasonable to assume that there's an exponential model at play here. Again, if they gave you a residual plot as well, you would have to put that in your description here. Here they didn't give you a residual plot, so you don't have to explain it, obviously. But if they did give you a residual plot, you need to use that in your description. So again, we're looking for randomness in the residual plot for a linear patterns, okay, for this. All right. So part B, give the equation of least squares regression line. So again, using the computer model, we have our A and our B. And remember that we're doing the natural log of y, so we have the natural log of y hat, right, for our model. So we got the natural log of y hat equals our A plus our bx, right? That's the A and B given in the computer output. Again, we got to define our variables. So what is y hat? That's the predicted number of transistors. What is x? That's the number of years since 1970. All right, so for part B, for part C, we're going to plug in the value for 2020, not here, not 2020 here. Remember, if we wanted to predict 2020, then that's 50 years from 1970, right? So we're going to plug that into x. So for part C, we're looking for 50 years since 1970 for the year 2020, right? So we plug that into our model. We get that the natural log of y hat is 24.9372. Now remember that the invisible base for natural log is e, okay? So here we got natural log of e, and the e is invisible because it's implicitly defined by the fact that we're doing the natural log, okay? Because e is known as the natural base. All right, and that's why this is called the natural log, because it's the log of the natural base. All right, so we got the ln of the natural base e of y hat. So we don't have to write ln because that's actually redundant. We can say that ln is the logarithm of base e, which is equal to 24.9372. And then again, remember the opposite of the logarithm is the exponential function. So we got to exponentiate. We got to turn both sides into an exponential, basically. So we're gonna do the base e, the natural base e raised to the left side power, and then the base e raised to the right side power. Okay, and that turns it into an exponential, and then we can cancel that out because those are opposites; they're inverses. So they cancel, and so we get y hat equals e to the 24.93 power. Remember, e is the number 2.71828 ... It's a number kind of like pi that goes on forever. It's the number for growth. So it usually appears in exponential models related to growth, like compound interest, things like that. So here we go. We get a lot of transistors here, 67 billion. 67.6 billion transistors. There's a lot of transistors here in 2020. That's the predicted amount. All right. This model predicts that an Intel chip made in 2020 will have about 68 billion transistors. This is the context. Remember that we have to include the context in our question. If you're doing this on the FRQ for your response, make sure you include the context when you answer the question. All right, so how to choose the transformation. Now we're going to show you an example where we have to decide which transformation are we going to do. Are we going to do an exponential? Are we going to do a power model, right? So which model are we going to use, exponential or power? Well, first off, what you can do is compare the models, right? So we could do the logarithm of x and then just leave y the way it is. We could do the logarithm of y and leave x the way it is, or we can do the logarithm of both and see what happens, right? And compare the models. So here, we're going to see which model is best. So model 1, you can see that model 1 is, for this example, so model 1 is just the traditional, right? So this is just the original data. So I'm going to put original. Actually, it says it here. So model 1 is original. And then for model 2, what we do is we take the logarithm of y, and then one of them takes the logarithm of y, and then the other one takes the logarithm of both. Okay, that's how they do it. So we got the original, we got the logarithm of y, and we got the logarithm of both. Okay, so this is the original data, and then this is the residual plot of the original data. Okay, then we take model 2. This is the log of both. You can see that there. We take the natural log of both. And this is braking distance for the car versus the tread depth. So if you know the amount of tread that's left in the tires, how is that related to the braking distance for the car? Is essentially what we're trying to look for here. So look at the residual plot here. That looks more random. It doesn't look to have a pattern like the other one did. So that's something to keep in mind. Model 3, we have the natural log of the y versus the x, or the natural log of the braking distance. I'm sorry, this is the natural log of x. Sorry, this is the natural log of x. Okay, I said the natural log of y earlier. This is supposed to be the natural log of x, not y. All right, so so the braking distance is going to determine, we're looking at the braking distance determining the tread depth here. So, all right, so it looks like there's a pattern here. That is not good when we're looking at models, right? We do not want to see any leftover patterns in the residual. All right, so let's compare the 3 models. In model 1, the original model, obviously the original model does not do the job because we have this pattern going on here in the residuals. We definitely don't want to see any patterns, even if there are 50% above and below. That's not the whole picture. We want to see, is there a pattern? If it's random, then it should be approximately 50% above and below, but it's not. That's not the only thing we consider. We want to consider, is there a pattern? Now here we can see that there's lack of pattern. There's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, about 50% above and below, which we would expect if it's completely random. Also, there's a lack of pattern in the residual plot. So it looks like if I toss heads, I would get maybe above, toss tails, I get below. So it's just kind of random, right? That's good. We want the residuals to be random. So in other words, when we make a prediction, it could either be heads we predict above what's actual, or tails we predict below what's actual, right? Sometimes we'll be spot on, like in this one, this looks spot on, right? 0 residual, that's usually rare, so that's usually not going to happen. But sometimes, sometimes it'll happen. And then we got model 3, we got another pattern here. Okay, so because the model that uses x equals natural log of tread depth versus natural log of braking distance, that's model 2. That produced the most random scattered residual plot, no leftover pattern. That has to be the appropriate model. So if it's natural log of both, that means we're looking at, so if we're doing the natural log of both, we're looking at a power model, right? So if you're doing just a natural log of one of them, so to repeat, if you're doing the log of both x and y, that's the power model, right? If you're going to do the log of the y, that's usually an exponential model. Now, if you're doing the log of x, right, then that just means you're treating it as a logarithmic model, right? So if you're just doing the log of x, you're saying, okay, well, I think the graph is a logarithm, and so I'm modeling it as such, right? So that's something to keep in mind. If you're doing the log of x, then you're actually saying, well, okay, y equals a log of x plus b, right? You're thinking it's some kind of log, and that's why you're taking the log of x, right? Sorry, I should have written it as a plus b log of x, right? Because, a plus bx. But yeah, you get the idea. It's a plus b log of x. And you're treating it as, a log, right? But in any case, it doesn't really matter because if you look at model 3, it's definitely not a logarithmic or exponential or anything like that. Has to be a power model. All right, so that seems to be the most appropriate model. All right, so then use the model chosen in part A to calculate the, this should say part B, by the way, not part A. For part B, use the model in part A to calculate and interpret the residual for the trial when the tread depth was 3/32 of an inch and the stopping distance was 13.6 car lengths. Okay, so this is the stopping distance, the braking distance, that was x equals 13.6. And we got the tread depth, y is 3/32. Now, remember we're doing the natural log of both of those, right? So in our model, we got to do natural log of natural log of this guy, or natural log of y hat equals a plus b natural log of x. Okay, so when we do this, we got the natural log of the y hat equals our a plus b, and then the natural log of x. Okay, where this is our a and our b. All right, so keep in mind that we're doing the natural log of both when we actually put the residual in, right? So it says that we want to calculate and interpret the residual for the trial when they give us those values, right? So it says the tread depth was 3/32 of an inch. So this is my actual, right? This is my actual tread depth. So we're going to find out where our y hat is by plugging in the okay, so I want to correct myself real quick that I just realized. So I said that the x is 13.6. That is incorrect. The tread depth is x. So I apologize for that. So the tread depth is x. The stopping distance was y. The tread depth, the depth of the tread in the tires is going to determine the braking distance, right? So I reversed that. So I apologize. So here we got the tread depth is 3/32 of an inch, so that's my x. But remember that if I look in the previous example, it says that the tread depth is measured in 1/32 of an inch, and so the x value is actually going to be 3 for that. Okay, so if I go back to this here, this is going to actually equate to x equals 3 because it's 3/32 of an inch. Okay, so let me erase this and change this to 3 because that's 3/32. So it's measured in 32nd of an inch. So in our model, so that's what this is assuming when we do the computer model, and it says that in the problem. And so the stopping distance is 13.6. This is the actual. So this is the actual stopping distance that they measured. So now that we got that out of the way, now we know that x is 3, so we're going to plug this into here. And then we're going to find out what our predicted stopping distance is. Our prediction is our stopping distance for y hat. And when we plug this in, we get 2.608. Again, remember there's an invisible e here, so we're actually going to do e raised to both sides, right? And so if we do that, we get e raised to the 2.608 power. That's 13.57 car lengths. So our predicted stopping distance for a tread depth of 3/32 of an inch, meaning x equals 3, is 13.57 car lengths. The actual was 13.6. So we can go ahead and calculate the residual. So this is the actual minus the predicted. Remember that to calculate residual, you take y minus y hat. That was in the previous lesson. So we get y minus y hat, so that's 0.03 car lengths. That means that we underpredicted, which means that the actual was over what we thought it was, right? We thought it was 13.57, but it was actually 13.6. So we underpredicted, meaning that it was actually over our prediction. So when the tread depth was 3/32 of an inch, the car traveled 0.03 length farther than what we thought, than what was predicted by the model. All right, so there's our part B, which is the residual. So now for the and that is it. So once we got the once we determined the model using the residual plot, then we calculate the residual. Now, if they wanted a least squares regression line, then we can go ahead and do that. If they wanted the LSR, so we can go ahead and we could do that now. Actually, we did the LSR earlier, I believe right here. Yeah, so we got the LSR here, and we calculated the residual. The only other thing I can think of is if they want you to do this on the calculator, you can follow the steps that we had earlier for doing the natural log of x and y. Okay. All right, and that is going to do it for the video, guys. I hope you found this useful and informative. As usual, I'll see you in the next one.